Okay, welcome to this month's CRC Cafe. Today our topic is going to be post-harvest, or otherwise known as drying and curing. We'll be looking at how to define terms and of drying and curing and what is happening during those processes so that we can optimize them and maintain high quality plants. So lots of things can happen as buds age, or they are dried and cured. This can go well or it can not go well, depending on the environment. And so, but before we get started, we'll define some terms. So drying is the process where water loss occurs until the buds reach the appropriate shelf-stable water content. And we use the term water activity of 0.6 is what our typical target is. And so this whole process until we get to that right water content is drying. And then after that, we are really no longer trying to remove water from the buds. And so that is the curing process. So that is post-drying changes that occur in bud quality. This could be describing how water becomes redistributed within the bud, becomes more evenly distributed in the bud. And it can describe changes that occur in the terpene profile. So for the most part, drying, we really understand that it's simply a physical process that, yeah, it's well understood. Curing, I think, is still quite the black box. We're not exactly sure of all the things that are happening during this process. We understand a few of them, and so we have a few good reasons for curing, but a lot of it is still a bit of a mystery as to how it changes or improves product quality. But we'll share with you today what we do know. So other terms that we'll be using is moisture content. And moisture content, sometimes if you look on the internet, you'll see it being expressed on a wet basis or a dry basis. We are talking about moisture content on a wet basis, and mathematically that is the mass of the water divided by the mass of the wet tissue. And there are three ways of measuring that. Perhaps the best, but also the most expensive, is to purchase a moisture analyzer. And this is basically a very high quality scale that has a little oven in the scale. So you put the tissue in, it weighs it, it bakes it very quickly over a minute, and then it reweighs it once all the moisture has left that tissue, and it gives you the moisture content quite quickly. So very nice, but several $1,000s. Another way one could assess moisture content is to use a wood moisture meter. These are used in the lumber industry to assess the drying of timber. And you can it's a handheld unit. You can take a handful of buds and put them over these two probes, and you will get a reasonably accurate number. So those are not particularly expensive. You can get them for under $100, and they can work. The third way of doing it is would require an oven, and it would require a scale. So we basically were doing what the moisture analyzer does quickly, but we would do this over time. And the process is outlined here. I won't go into it in detail, but basically you weigh the tissue when it's wet, you bake that tissue in the oven, and so you can calculate the moisture content of that particular crop and that tissue that you're going to be drying. And so you know how much water is in that tissue. Then you have some sample tissue that you dry, and every day or how often you want to measure moisture content, you can continue to weigh that tissue, and now you know exactly how much moisture is in that tissue because you've already baked some to see how to get rid of the water and to know how much water is in the tissue. So now you can, on your samples, you can be drying them and weighing them, and you are going to know when you hit your target moisture content. So anyway, the math is there. It's actually quite simple. You do have to have bake some tissue, so you lose that tissue because you get, take all the moisture out of it, and then you have some samples within your drying room that you continue to measure during the drying process. So that can work well. The cost of it really depends on how good of a scale you have. Clearly, the higher the resolution, the scale, the better the numbers are going to be. But a scale that measures 0.1 grams or 100 milligrams should be quite sufficient for this. Kitchen scales that only weigh 1 gram, have 1 gram resolution, are not going to be great unless you have a large sample. So if you're measuring relatively small amount of tissue, then you want something that's going to measure 100 milligrams or even 10 milligrams, but which each decimal place of scale becomes more expensive. Okay, continuing to define terms. Water activity, abbreviated A subscript W, is the ratio of water vapor in the tissue and the water vapor of the surrounding air. So, and that being at equilibrium. The math is shown here. So you record the water vapor of the tissue and the water vapor of the air, and when this sealed jar of buds is at equilibrium, where there's no longer any movement of moisture out of the buds into the surrounding air, then this is the water activity. And so initially you put buds in a sealed jar and water is going to evaporate. That process stops when the water pressure in the air is the same as the water pressure in the leaf. So water keeps leaving the leaf, the buds. Water keeps leaving the tissue until there's this equilibrium. And so at this point, then what you do is you measure the relative humidity of that air. So you have a humidity probe, for example, that's inserted into this jar, and that relative humidity in a is the same as water activity. So if you measure 60% relative humidity, that's 0.6 water activity, and that is, of course, our goal. That then we have a shelf-stable product that is not susceptible to growth of bacteria and fungi. So when you hit 0.6, biological activity ceases. So these would be bacteria or fungi that are ceasing to grow. You're not actually killing them. So you're not, they're still there. They're just not going to grow. So if you have something that actually is like a human pathogen or something in there, so like, for example, if you had E. coli, you're not getting the water activity down to 0.6 does not get rid of that bacterium. It just keeps it from growing and becoming coming to a population size that might be more harmful for human consumption. Okay, so water vapor pressure is a measure of the pressure of water molecules, and this term is useful in that it helps us then calculate VPD, which we'll talk about in the next slide. What is important to understand is that the activity of that water, the movement of those water molecules is influenced by temperature and humidity. And so this is our curve showing temperature increasing from basically freezing to about 100 degrees Fahrenheit. And you can see, as in a 100% relative humidity situation, you have water vapor increasing quite fast as you increase temperature. So it's increasing at an increasing rate. If you have 50% relative humidity, the water vapor pressure is 50%, is half of what it would be at 100% relative humidity, but it still is increasing at an increasing rate. So warmer conditions, higher humidity conditions create higher vapor pressures in the bud tissue or in the air. And so where this is useful is calculating vapor pressure deficits, which is by definition, the water vapor in the tissue pressure minus the water vapor pressure in the air. And so this difference between what's in the plant tissue and what's in the air drives the rate of evaporation from the tissue to the surrounding air. So it's the thing that is directly driving the drying process. Okay, so vapor pressure difference or vapor pressure deficit is the difference in water vapor pressure in the tissue and in the air. So what this looks like, you can visualize it here. This would be a high vapor pressure deficit situation. You have tissue that is fairly wet, has a lot of moisture, and air that is fairly dry. These little blue water molecules here are at a much lower concentration or lower pressure. And so water is going to leave that tissue quite rapidly. And because there's this big gradient, there's a large difference between the two vapor pressures. So water volatilizes quickly. In a low VPD situation, you have, here's the bud with water vapor pressure fairly high, but the surrounding air also has a high water vapor pressure. So the difference is not that great. And so that's a low vapor pressure deficit. And so much less water moves much less quickly, and much less water is going to move from that bud to the surrounding air. So when we talk about drying, what we're trying to control is this situation, the humidity in the air, and we do that by controlling temperature. We're really trying to control the vapor pressure in the air and control the vapor pressure difference between the tissue and the air by managing temperature and humidity. So this would be an example of how buds dry over a 7-day process. Here we start out with 100 grams of tissue. When we bake that tissue in the oven, we find that 22 grams is dry mass, and then the other 78 grams is water. And so these buds, as we dry them, cannot get lighter than 22 grams. So that's kind of our bottom line. Our buds dry, and as they get drier, that vapor pressure difference becomes less because the vapor pressure in the tissue is lower. So the vapor pressure deficit, the difference between the tissue and the air, is as a smaller number. And so you see the rate of drying is decreasing as you approach a completely dry situation or zero moisture content situation. So the risk of botrytis as these buds are at different moisture contents or water activity numbers will vary. So when you first take a wet bud that has a water activity of near 1, our risk of botrytis is really high. You take those buds and seal them in a jar so that they cease drying, and you'll have botrytis grow very prolifically, very quickly. As the water activity decreases, the risk of botrytis becomes less and less. It's going to be even you have spores on the buds all the time. Probably you really can't prevent botrytis spores from landing on buds, but the ability of those spores to germinate and to grow is going to be affected by how moist the tissue is and for how long. So the faster we dry the tissue, the faster we get down to 0.6, we reduce our risk of botrytis. The spores that are already there, we're reducing the risk of those growing and ruining the tissue. So when we have a drying environment, we really want to be managing this vapor pressure deficit. And so a common combination of temperature and humidities that is used is for growing a lot or for drying a lot of cannabis products would be a temperature of 60 Fahrenheit and a relative humidity of about 60%. So that 60-60 is kind of a nice ballpark starting point when you're drying. And so the numbers here reflect the VPD, or the vapor pressure deficit, that you would expect to achieve in buds that are in this environment. So for example, the 60-60 combination gives us a VPD of a 0.59. Well, this table shows you, a lot of different possibilities with a range of humidities and a range of temperatures. And of course, we can have even much higher temperatures than what are shown here. But what this table shows you is that what you would expect is that if the vapor pressure deficit is 0.59, it doesn't matter what the temperature and humidity combination that you have, you would expect those buds to dry at similar rates. And so, for example, if you drop, for example, if you had the humidity down at 40% relative humidity, and the temperature was 48 degrees Fahrenheit, 9 degrees Celsius, that number is 0.6, so it's essentially the same. So you would expect the same drying rate at a, what did I say, 46-40 situation than you had a 60 Fahrenheit, 60% relative humidity situation. So you can choose other combinations of temperature and humidity to accelerate or deaccelerate the flowering process. So as the numbers are bigger here, the VPDs are bigger on this corner of the graph. For example, this point here, 62 Fahrenheit and 10% relative humidity, the VPD is 1.56. So that is almost 3 times higher than our 60-60 situation. So you would expect the water to leave the buds 3 times faster. And so we would reduce our drying time significantly by having plants in with these higher VPDs. If we get down here, these low VPDs in the upper right-hand corner, you would expect you're going to be slowing the drying process significantly. And what that looks like is something like this, where we have moisture content over time. And I've put in 6 different combinations of temperature and humidity. So we go from the coolest temperature is 41 Fahrenheit, 55% relative humidity, and the highest humidity for this example is there. The warmest situation is 77 degrees Fahrenheit, and the lowest humidity that I programmed in was 30% relative humidity. So you can see the VPD here is 2.2. On the other extreme, the VPD is 0.4. And if we look at those curves, where the VPD is 0.4, this bud dries at a rate something like this. So over 19 days, it takes to get down to about 10% moisture, in this example, 9% moisture content. Those same buds placed at a VPD of 2.2 dry very rapidly. And so in 3 days, we can achieve that same moisture content. And of course, there's then other combinations that are in between. So, well, what do we really want? Well, one way to look at this is, well, if we dry buds very quickly, or I say too fast, you're going to have less uniformity in the buds. The outer surfaces are going to get very dry. The inner part of the bud's going to stay moister. So you're going to have a gradient of moisture within that bud. And then the outer part may be getting too dry, and that can harm quality. And when this is almost like landing a plane. If you're coming down very quickly, you can imagine it's much easier to overshoot your target moisture content. So if we're targeting 10 to 12% moisture content, which is often the case, we may overshoot that and get the buds too dry, and again, reduce the product quality. So one could, well, let's look at the other example, other extreme here, where if we're drying too slow, where it's now taking 2 weeks to dry, that might be fine if there's no botrytis spores in your buds, but the more botrytis is in there, or some other harmful microorganism, the more likely it has more of a chance to grow, because you're not reaching that low moisture content needed to inhibit biological activity. It's taking time. So then there's kind of a sweet spot in the middle here, and that we kind of makes it easier for us to where we're drying as quickly as possible, but not too dry, not too slow. So we're not giving botrytis a chance to grow. If you're having botrytis issues, this is clearly a tool where you can reduce that VPD or increase the VPD so you get a steeper dry down curve. Of course, you don't have to have the same temperature humidity throughout the whole drying process. One could start with a warmer environment and dry fast in that first day or two when you're just trying to take out a lot of water quickly. And then as you're landing the plane, you decrease the temperature so that it's a more gentle coming down into that target moisture content percentage of 10 to 12%. So most people I talk to seem to like to dry for 1 week. This is desirable because you're harvesting weekly, and unless you have 2 drying rooms, you're wanting to get the tissue out of the drying room so that you can put in the new tissue, the new harvest. So to be able to cycle a drying room once every week is kind of ideal. If it takes more than 7 days, it kind of causes some challenges unless you have some additional space someplace else. So, there's some benefit to drying on a little bit on the warmer side. And I've heard of facilities that dry really warm over just a very short period of time. Often those facilities are not that interested in the terpene profile though. So if we dry at high temperatures, we do decrease the drying time, but and actually that can be beneficial for cannabinoids because they're not so temperature sensitive. So the faster we dry, we preserve cannabinoids a little bit better under warmer temperatures. We do increase the potential of over drying, which is a significant qualitative measure. We also, higher drying temperatures will increase the volatilization of terpenes. And so if terpenes are an important part of your product, then you might avoid drying at excessively high temperatures. So it depends, are you selling cannabinoids or are you selling some combination of cannabinoids and terpenes? If you want the terpenes, then cooler drying temperatures are desirable. We lose terpenes under all situations, we just lose them less quickly under, at least we lose the really highly volatile ones less quickly if the temperatures are not so warm. The other thing that we don't have a good handle on yet, we just have some anecdotal observations, is that high wind speed or high air velocity during the drying process appears to be detrimental to terpene volatilization. Meaning we've observed that when we dry under with a lot of air movement, the buds come out of those drying rooms with with an inferior fragrance. Often it's kind of grassy or a bit of a dull fragrance, or not very fragrant at all. And again, we haven't had good controlled studies to prove this yet, so that this is a topic that we are studying this semester, and so it's currently being explored. We'll have more information hopefully by January. So that's the drying process. Of course, there's a lot of different ways of growers do it, but the principles are there to apply to your specific situation. Curing is, now we've gotten the moisture out that we want, then we put the buds into a sealed environment, a bin or a bucket of some sort, and those typically get burped on multiple times a day on the first few days, or daily for the first week, or sometimes more than a week. We'll call that purging or burping. It hasn't been clear what the purpose of that is, but we have some data to show you what I think reveals at least one of the reasons you might want to why burping is probably a good idea. So this is another picture of of a bud. And so when we do rapid drying, so we start out with a bud that's uniform, harvested off the plant, so there's equally equal moisture distribution. But if the faster we dry, the more we end up drying from the outer shell or the outer layers of the buds, and the moisture from the inside of the bud does not diffuse to the outside as fast as the moisture on the outside evaporates. And so we end up getting this bud to what seems to be a good moisture content, and the water activity may initially be a good number, but the water is not uniformly distributed. And so what you find over the next week or two is that this moisture does diffuse out to the outer margins of the tissue, and then it actually will go out into the environment too. So we can actually have some increased water loss from that bud after time, whereas initially it looks like it's completely dry bud. And of course, this is more of a problem if you are bucking after drying. If you're leaving the flowers on the stems during the drying process, then there's obviously more moisture that needs to be removed, and the moisture from the stem tissue doesn't necessarily come out all that fast, or as fast as from some of the bracts on the flower. So if you're bucking before you dry, this is a little less of an issue, but it still could be an issue. And so what happens then, if we take this bud that has these layers of moisture and we place those into a sealed jar, and say the initial water activity is 0.6, what you may see over time is that some water then, after this bud becomes uniform moisture distribution again, then some moisture then will volatilize from the outer margins of the bud. And so the data that reflect this are from this simple experiment where we're actually measuring relative humidity, but if you remember, that is the same number as water activity, except you put a decimal point before the number. So 0.69 humidity is the same as 0.69 water activity. So what we did, we dried buds down to, we had numbers about from 0.67 to 0.69. We should have gone a little bit lower, but in this experiment, we stopped drying at this point, and we put the buds into sealed canning jars. And then we did a daily purge versus leaving the buds sealed. And we would measure humidity in those jars daily for 28 days. And so there's 28 days in the curing environment. And what you see is pretty clear here. Where we purge, we continue, you see the humidity continues to come down. So that means the buds were continuing to release moisture to the air. And then by doing the burping process, we are off gassing what is in that sealed container, sealed container. And so our numbers continue to come down a little bit over a month. In contrast, where we didn't purge, you actually see the numbers climb a little bit as moisture again comes out of that bud. And now, since we're not purging, the moisture accumulates in the vessel. So this clearly shows that moisture is continuing to come off of those buds after we've dried them, and and so the process of purging the curing vessel is useful to really removing that excess humidity. So I think this is clearly a benefit that happens during the curing process. But being in a sealed vessel, this water release is much slower than if you left them in the drying room for another day or two. So, you never take them, you pull tissue out of the drying room and it's not completely uniform. And so this, again, allows you to, it's a little bit of a buffer. You don't want to leave product in the drying room too long, but then again, it's not completely uniform. So by putting it in a sealed vessel and off gassing daily allows you for that product to become more uniform. And if you happen to pull the product out of the drying room maybe a little bit too soon, it's an opportunity to get that little bit of excess moisture out of the product. So again, you don't have organisms growing. So that's a good reason to purge during curing, and it's something that is happening during curing beyond really the drying process. The other thing is that happens potentially under curing is the terpene profiles are going to change. So we're calling this the fate of terpenes. So we have our jar here with buds in it, and what we did was kept them sealed in this jar, and then we would measure the terpenes in the headspace. So that's what is volatilizing from the buds, and we measured the terpenes that were in the buds after period of time. I think we had them in there for a month, and what the general theory is that, and our data support this somewhat, is that the monoterpenes are much more volatile, and so that is primarily, those are the things that you're going to measure in the headspace. Whereas in the buds, the sesquiterpenes are much less volatile, and so they're going to remain in the tissue. And then when this product is eventually ignited during the smoking process, what we expect is happening, and we don't have data for this yet. I'll show you data for the part on the left, but what we think it happens is that primarily when you're igniting them, a lot of the monoterpenes may be gone, or they're at lower concentrations, but the sesquiterpenes certainly have not volatilized yet, and so those might be the ones that you really produce the fragrance during the smoking process. And what the data look like are these here. It's a little complicated, but just bear with me. On the x-axis is the terpene concentration in tissue. So in the buds themselves, we go from 0 to high number over here. The number's irrelevant, but you go from nothing to a high number. On the y-axis is the terpene concentration in the headspace, and again from 0 to a high number. The number is again irrelevant. It's just kind of a relative scale, and each dot represents a different terpene. Okay, so that is tested. And so we test the terpene in the headspace, we test the terpene in the tissue. And the blue dots are the monoterpenes, and the orange dots are the sesquiterpenes. And so there's a few things that don't quite fit with theory, and so we don't understand them, but in general, the theory holds. What you see, first of all, is that beta caryophyllene and alpha humulene are actually quite high in the headspace and the tissue. And these are sesquiterpenes, so we would not expect them to have been this volatile, because they're pretty volatile in that you are sensing them measuring them in the headspace. So those are kind of outliers, and that I can't explain very easily. But if we look at these other 4 sesquiterpenes, you'll see they are all basically 0 in the headspace, but they are, well, valencine is pretty low in the tissue also, but alpha bisabol and guaiol and caryophyllene oxide are higher in the tissue, but none is in the headspace. And that's kind of what you would expect with the sesquiterpenes, is that there's plenty of them in the tissue, but they're not volatilizing. In contrast, all the monoterpenes, you don't see any big numbers in the tissue. What you're seeing is primarily bigger numbers in the headspace. So and you don't see any that are at 0 in the headspace. They're all volatilizing. And so we take an example, this first one, linalool, which is the lavender scent, I believe. Very high headspace, very low tissue. So all the linalool has gone into the headspace, and there's very little left in the tissue. We have 3 here, terpinolene and a couple others, where there's still some in the tissue. As you can see there, the number is not 0 on the x-axis, but they're also volatilizing. And then you have another group here with myrcene and borneol that are volatile, and then there's one other group here that is just low. involved in the headspace and the tissue. So in general, with the exception of these guys here, the beta caryophyllene and alpha humulene, those are the ones that you are most prevalent in the headspace. Now, we would assume those are the ones you're smelling the most. That might not be true. It could be that you have compounds that are very easily perceived at very low concentrations. But these are the ones that are certainly the most dominant in the headspace. And then you have others that are definitely most dominant in the tissue and have nothing in the headspace. So they're not volatile at all. So that's pretty neat. This is just a first experiment, but I think it shows some interesting concepts. The other thing that's interesting to me is we have dried buds in various ways and gotten buds that are quite fragrant, and others that really are much like a hay or grassy scent that is not very impressive and not very substantive. And we've run terpene analyses of the headspace of these tissues, and my expectation was for the not to really perceive or much any terpenes in the headspace of the ones that didn't have much fragrance, and the fragrant ones would be much higher headspace numbers. And so these are our list of several dozen terpenes, and you see the comparison bar graphs. And on all of these, for the most part, the fragrant ones are consistently higher in the fragrant buds compared to the less fragrant buds. But the less fragrant ones still have pretty significant numbers. There's maybe we calculate here, most of these are 5 to 15% higher concentrations with the fragrant ones, which is significant, but I would have expected a much bigger number, and that these ones that weren't, the orange bars, the ones that weren't very fragrant, I expected that to not be nearly as high as it was. So there's still a lot to be learned here that we don't understand about fragrance and cannabis and terpenes, and but it's some interesting data to start to think about. The last slide for today is again thinking about curing and what else is happening. Certainly the moisture content is being redistributed in the buds during curing. Certainly the terpene profile is changing no matter what we do during a curing process. And whether that is a good thing or a bad thing, we're not controlling it very well, and don't understand what we even want other than trying to maintain the terpene content as high as possible. Oh, the other point I want to mention too is that when you assess total terpenes, that doesn't necessarily translate into highly fragrant tissue, because again, these guys here that are on the 0 line in the headspace, they're not going to be very fragrant at all in that tissue. Maybe they are once you ignite the tissue, but you're not going to open up a jar and smell those because they're not hardly volatile. So when you see a product saying it's 1 or 2% terpenes, I don't know that matters. It depends what terpenes you have. Yeah, and it could be the medicinal value of terpenes is from primarily these ones that are less volatile, because they're the ones that you are more likely to be consuming. The ones that are really volatile certainly improve perception of the product when you're smelling it, but may not be something that is necessarily consumed days later after it's purchased. So, okay, back over here. So we know there's some things that we do with curing, but other things that could happen during curing that could be beneficial to one's, for example, smoking experience. If we look at tobacco, where there's a lot of research has been done on curing, we see that over that curing process on tobacco, there are changes in the carbohydrates, the sugars and starches. There are changes in the organic acid compounds, and there's changes in the pH of the tissue. And all 3 of these have been correlated with quality perception in smoking. So reducing organic acid, reducing pH have been attributed to through experimentation to actually improve smoking perception, or create a smoother smoke, a less harsh smoke. And so there's some benefits there. Now, are those things occurring when we cure cannabis? We've tried to measure some of these, and so far we don't see any real difference. But again, there's still a lot to be learned here, and a lot of potential to understand what qualitative characteristics may be occurring during the curing process. So that is what I have for you today. I believe next month we'll be talking about flushing. Mike Alden will be doing the presentation. He's been doing quite a bit of experimentation looking at how what benefits there may be in flushing at the end of a crop to improve quality, and he'll show how that affects yield also. So we will see you next week, and thank you for your time.